Hello and welcome to Module 3, Concept Generation, Functional Analysis, System Architecture, and Design. In this module here, we will talk about functional analysis and allocation preliminary design. Referring back to Figure 2.4 from Blanchard and Fabricki, here we will be reviewing the allocated baseline. This is the output from the end of the preliminary design. Recall that conceptual design ends with the functional baseline. This functional baseline leads to the allocated baseline, and the allocated baseline in turn will eventually lead into the product baseline at the end of the detailed design and development. After that point comes updated product baseline, which is the final milestone before eventual operational use. While we will not go into that level of detail within this course, the IE452X System Engineering and Analysis course will go into that in greater depth. The major steps in the functional analysis and allocation process are the functional architecture, beginning at the top level as a set of functions that each are defined in the applicable requirements document or specifications, each with functional performance and limiting requirements allocated to it. Then, the next lower level of the functional architecture is developed and evaluated to determine whether further decomposition is required. If so, then the process can be repeated. If not, then the process is completed and the system synthesis can begin. These are all available in the INCOSE Systems Engineering Handbook. At each level of the functional analysis allocation process, alternate decompositions and allocations may be considered and evaluated for each function and a single version selected. After all the functions have been treated, then all the internal and external interfaces to the decomposed subfunctions are established. Recall from developing problem statements that it was important not to lead with a solution. For example, saying the processor does not compute at XYZ speed doesn't pigeonhole you the way a problem statement of older processor prevents computation at XYZ speed. They sound very similar, but there is a big difference. In the latter case, the only real way to address the problem the way it's written is to upgrade to a new processor. While that may work and solve the problem in the first case is more open-ended and leaves a number of other options at our disposal. It could be possible to still meet the speed requirements by redesigning the components, adding redundancies, or finding some sort of trade-off at the subcomponent level. In the first case, we have a multitude of potential solutions at our disposal. This figure details the process of developing alternate decompositions. First, break the function into subfunctions. From there, you will decompose the requirements and allocate them into the appropriate subfunctions. This will be an iterative process in and of itself as you develop alternate decompositions. Eventually, you will evaluate the alternate decompositions and select the ideal one. Of course, depending on the output of that analysis, you still may need to step back and update requirements within the subfunctions and repeat the process again. Now consider functional analysis is the technique of identifying and describing all the functions of a system. The purpose is to identify and partition all the functions of any system required to perform the intended purpose. Take, for example, the European Cooperation for Space Standardization. The intent of their initiative is to establish universal standards for space exploration. Consider all of the possible subfunctions for space exploration systems. Conducting functional analysis in this case could be an extremely labor-intensive exercise. It would be very time-consuming to update all the interdependent subfunctions. At the same time, the criticality of doing it right and doing it properly becomes even more important with a larger scale system. As a general rule, the larger the system, the more important it is to do functional analysis correctly, while at the same time functional analysis becomes much more complicated and difficult to do. Let's talk now about the objectives of functional analysis. Identify or updating the functional requirements, which we have already discussed. Ensure that functions are partitioned in an appropriate manner. Ensuring functions are partitioned appropriately can be more difficult than it sounds. The larger your system, the more subsystems you would have. Incorporating appropriate design across all these subfunctions and subsystems can be a very detailed process, particularly with regards to the iterative nature of it. Allowing traceability of the function. Traceability is important, particularly given the iterative nature of system design, as a trade-off is made to the traceability needs to be maintained in order to understand the impacts. This is especially necessary for future review when changes must be made again or questions arise as to why the function was designed the way it was. And identifying interfaces between the functions. This refers to how information is transferred between functions. The steps to implement functional analysis are first to define the system and the boundaries. Defining the level of detail and depth analysis, both of those first two go right towards the scope of your effort. Then identify the system functions, operational modes, and operational scenarios, and then finally, representing the system. Let's look at functional analysis implementation in a little bit more detail. Starting with the inputs. This includes the requirements and constraints. Next is the activity. Here you need to define the system using those inputs as a guide. As a sub-step deliverable, you also need to define the level of detail given the input requirements and resources available. Last is the outputs. This should result in a defined system and appropriate interfaces. It also includes detail of the functional model. Here is an example. Starting with the inputs in this case might be the mission phases, and operational sequences. The activity then starts with identifying those functions. From there, there's a detailed double-click, which would be a tree model, functional matrix, and block diagram. The output would be the completed models from each of the activity levels. These are some of the methods for functional analysis and allocation. We'll talk specifically about the functional flow diagrams in the next few slides. The others are all good to keep an eye on and understand that may be applicable, however, will not go into great detail within this course. Functional flow diagrams are one of the best tools for functional analysis. They may vary slightly in appearance based on a particular industry or organization. Ultimately, however they look, the intent behind them is very consistent regardless of the particular application. In all cases, they should be multi-tier, time-sequenced, and a step-by-step diagram of the system functional flow. They are usually prepared to define the detailed step-by-step operational and support sequences, but they may also be used effectively to define processes in developing and producing systems. In the system context, the functional flow steps might include combinations of hardware, software, personnel, facilities, and other procedural data actions. Rules for functional flow diagrams. First, the top-level functions should be numbered with integers and 0 decimals, for example, 1.0, 2.0, etc. And those should cover the complete span of lifecycle functions anticipated from initial setup and checkout through disposal. The reason that those need to be at the top level at 1.0, 2.0, and 3.0, etc. is to leave space for the subsystems in your numbering convention. Inputs to functions come from the left side, outputs from the right side, and lower-level functions emanate from the bottom. The name of the function is defined inside the box, replacing function A, function B, etc. A reference function is indicated at the beginning and end of all functional sequences. The lone exception to that is at the very top level. An OR gate is used to indicate alternate functions, and an AND gate is used to indicate summing functions, where all functions are required. A go, no-go sequence is indicated by an arrow out the right side with a letter for G for go and an arrow at the bottom side for G bar for no-go. Those last two, the OR and go and no-go, are very common to logic-based flow diagrams and are one of the main rules of these functional flow diagrams. And it is customary when at the second level or lower is shown on a separate page to list the title of the function either at the top center of the page for reference. This is usually more of a notation factor because when you get into the detail beyond that top level, it can get very cumbersome and complicated, and it's almost impossible to show at the appropriate level of detail with all the subcomponents once you get past that first level. Here's an example of a level 1 functional flow diagram. You see the steps being launch, ascent into orbit, checkout, deploy, and payload, transfer to ops orbit, etc. 0.0, 1.0, 2.0, it follows that individual convention. It has the and/or component here, and is also a very high level. The intent at the top level should be very simple and straightforward. This is a level 2 of functional flow diagram, and see it's the slight level below, a little bit more detailed and intricate, and is less at the macro level and more into those details. Transfer the ops into orbit, and then you see how the letters go to, or the number convention goes from 4.1, 4.2, 4.3. It still follows a logical flow sequence and still uses and/or type of systems, but it is more detailed than the top level. In the third level, is even more detailed yet. In this case here, you know how it takes section 4 of the level 1 diagram and blows it out into even greater detail. This would be the micro level compared to the macro from section 4.0. In summary, functional flow diagrams provide an understanding of the total operation of the system. They serve as a basis for development of operational and contingency procedures. They pinpoint areas where changes in operational procedures could simplify the overall system operation. They help develop requirements and to identify profitable trade studies. And they incorporate alternate and contingency operations which improve the probability of mission success.